I'm very happy to welcome Zeyneb Magavi to join us today at the Wilson Forum this morning. Zeyneb is the co-executive director of the Climate Solutions Incubator known as HEET, the Home Energy Efficiency team. Their focus is to find alternatives to fossil fuels, and in particular, a transition to geothermal networks, which I think she'll talk with us about today. HEET is, in my view, a model for community engagement to address socially important issues. And nothing is more important, I think, today than climate issues. Well, maybe I'm overstating it. There may be other things that are troubling in this world today, but certainly from the point of view of the globe, the issue of climate and energy needs is just crucial. And I'm happy to have you to welcome Zeyneb today to join us, and I'll turn the floor over to you. Welcome.
Thank you so much. I can tell already that this is a really fun group. I'm here with fellow geeks, and I'm already wishing that in my already too large slide deck, I'd added more slides, like on the chemical components of gas that come into your stove, etc. But I already have too many slides. And just to your first comment, long ago, I think it's 1990, I won the Massachusetts State Science Fair by building a weighted fiber composite flywheel as a battery for electric cars, which clearly didn't exist yet. And then I went off and did all kinds of other things, global health, et cetera, worked for BBN Technologies. So this is like a mid-career career change for me. And I've come right back to what we most need to do, which is solve climate. So let me see if I can, now that I've done that, actually manage to share my slides. It's always the trick here. And what I'm going to try to do, because I can see that the conversation is going to be the really fun part, I'm going to attempt to skim lightly over my slide deck. Yeah. To give you a sense of, right. There we go.
Yep.
To give you a sense of the different things we could talk about, and then try to keep it constrained to like 40 minutes and have enough time for conversation. So that said, so much fun stuff to talk about. All right. Let's see if it works this time. All right. Thank you, Google.
Perfect.
All right.
Thank you.
So, the valve on the right is a geo valve that's in the ground in Colorado. Just to give a brief sensationalist title, I'm here to discuss the birth of thermal utilities. I want to mention that HEET takes no money from any related industry. That includes gas and geothermal. We are grateful to our foundations that fund us and our nonprofit donors, and that allows us to have independence. Just to verify, very recently this past month, MIT Technology Review made this kind of bold statement that these networks that I'm about to discuss are becoming crucial to the US's energy future. We still have work to do, though, despite the fact that this is now launched, because their image has pollution coming out of the chimney of a house supposedly connected to a thermal network, which is a slight flaw. So I'm going to start from the beginning a little bit and use a hand-painted video from one of our employees to do what the hell is this thermal network thing? Brief 1-minute video. I'm going to pause it and, again, hopefully
right beneath our feet, the Earth is soaking up energy from the sun, and it's been doing this for a long time. Near the surface, the ground warms and cools with the seasons, but lower down, it stays at a constant temperature. In Massachusetts, that's 55 degrees Fahrenheit year-round. This stored temperature is a source of renewable energy. It can be accessed to heat or cool a single building without using fossil fuels. But did you know we can also connect entire communities to that renewable source in the ground? How does it work? It starts with underground pipes in the streets, sort of like gas pipes, but filled only with water. The water absorbs the ground temperature of the earth and delivers it to buildings. Pipes connect buildings with different heating needs, so energy is never wasted. Instead, it's exchanged between buildings or stored in the ground until it's needed. Inside, a heat pump moves heat in or out according to the temperature you want. This system of pipes can connect like Lego blocks, gradually moving us all from gas to geo, giving us cleaner air.
And I'm going to pause there. I just think it's super valuable. It's a basic public facing.
Right beneath our feet. So
Yeah. Yep. It is a public facing, and I can't. 1 second. There we go. And there we go. Video for the general public, but I just think that the visuals are so useful for learning for a lot of people. So that's a brief intro to what it is we're talking about today, but I want to back up now and talk about how we got there. Because HEET really attempts to very clearly and very consciously and persistently take on problems as part of a larger system. And this systems change approach, both social and technical, or socioeconomic and technical, means that we prioritize stakeholder engagement, which was mentioned earlier. Every core stakeholder is to us necessary to engage in order to solve the system. And finding the leverage points in the system, the places where we can get the most impact for a small amount of effort, and then finding innovations, iterations, or solutions to those while engaging with the stakeholders on them. Basically, until we find a way to move forward that has the minimal resistance and the biggest impact. And all of that moves at the speed of trust based on the relationships with the stakeholders. That sounds simple. It is so incredibly challenging. And I just want to comment, I love this cartoon. And I think if we call the elephant our future energy system, we simply have to admit that today we do not know what that elephant looks like. And we're an awful lot like these scientists. And whatever section we're thinking about is the part we're describing. So what we really need is all of them talking together and imagining what that elephant could be. And a geekier way to look at this is to really think about the way we study our future. And here's, a set of plans for decarbonization for Massachusetts. And what we did is we took a couple of different components of our future energy system and asked what the plans actually took in data and evaluated, and then mapped it to give you a sense that not unlike the scientists with the elephant, what we look at, measure, and think about is what we then imagine for the future. And there are parts that maybe we aren't looking at. And the part we aren't looking at to an enormous degree in so much of our energy planning, both in Massachusetts and at the federal level, is thermal. So I know you're doing an electric grid dive, but I want to point out that the electric grid is very, very connected to all of our heating, cooling, and otherwise thermal energy. And yes, we're still on elephants. Heating, heating our homes is the biggest elephant in the room in climate. We have not solved it explicitly. The air source heat pump, as someone mentioned earlier, is a phenomenal piece of technology, and there are challenges deployed at system scale. So we love the largest challenge in the room, and we took this on in about 2015. I want to describe just how big this challenge is for about a minute. These are emissions reduction commitments. Remember, legislative and regulatory boundaries tend to set and drive innovation, right? And we are committed in many places and really just ethically as a human society on this earth to emissions reductions. What does that mean in the US when it comes to heating? Well, we have about 111 million buildings, and that's about 12,200 square miles of conditioned space, which is roughly the square footage of Maryland. So we basically have to electrify or decarbonize an area the size of Maryland by 2050, which is about 3,400 buildings a day for 27 years. That's a lot of buildings. Sorry, I apologize. I skipped something. It's 3,400 buildings at 33%. It's about 10,000 buildings. But I was saying that even if we took on a third of that it would be 3,400 buildings. So I've actually underestimated. I apologize. It's a gargantuan problem. So bringing us a little locally, one of the many projects HEET has worked on is with our local gas system and mapping both gas leaks, and in this case, mapping our gas pipe replacement. Because even as we're taking on the decarbonization challenge, we have an aging thermal system currently. And that's what our gas network is it is a thermal energy delivery system. Of course, it's chemical energy and we're combusting it to make thermal energy, but whatever. So these are, each of these little dig icons is a pipe going in the ground in the next 5 years. And our shared estimate of all of the money spent on new gas pipes is close to $40 billion. That is even though we have a climate law that explicitly declares we cannot use those gas pipes by 2050, and it takes 40 years to pay off a gas pipe currently, even if we don't lose gas customers. So essentially, we've got a utility death spiral set up. And it's a little worse than that. First of all, I just want to acknowledge I'm sure many of you in Massachusetts are very aware of what happened in Merrimack Valley in 2018. 71 simultaneous house fires and 8,000 homes, overpressurized gas system, and a young man lost his life, all because one of those pipes going in the ground got a slight human error and the system overpressurized, a low pressure system. So could talk a lot more about that, but the risks are very real when you're dealing with a gas system and combustion. And we tend to ignore that because we live with it. But this is essential to consider and weigh in any transition planning, and too often it's left out. So another challenge to transition planning for thermal is that if we go at it the way our state and most of the country is currently imagining we do, plucking homes off to an air source heat pump one by one as people have the means and motivation. Each of those, and I'm just going to do it here. Here we go. We're electrifying people, and home by home. And what is happening as we watch? We have a smaller and smaller ratepayer base for a fixed infrastructure cost. We got the same number of pipes in the ground. We just don't have as many customers to pay for them. So this is a classic utility death spiral. It's a 4-letter word in the utilities. So I say it often. And this is accelerated by the amount of money going into new pipe and needs to be addressed. And so basically, to come back to that stakeholder engagement I mentioned, which I'm not going to do very often, but this is the core list that emerged from widespread stakeholder engagement of what was needed by any new system in order to allow every core stakeholder group to be willing to move forward. And it's quite a list. We got the ones in bold on the left put into law as mandates for our Department of Public Utility, because that was fun. And we tackled this systematically, trying to find solutions that would address all of these. And we got to like 8 and then 9, and then finally that network gas to network geothermal transition, or gas to geo transition, actually has a chance of addressing every single one of these. And that's why we're talking about it today. And I just have to clarify, I'm sure you've all heard about things like hot rock geo and enhanced geothermal systems and all of these things. I just want to apologize for the terminology. We have a terminology nightmare on our hands and we haven't solved it yet. Geothermal is stable, non-intermittent energy from the earth. Done. There are at least 4 geothermal technologies. That geothermal power with hot rock, think Iceland, is way on the left here. There's district geo where you didn't quite find hot enough for power, but you've got hot water, so why not make a district energy system? That's second there. There's building geo, which you've undoubtedly got some friends or a school that's put in boreholes and is on geothermal ground source heat pump. None of that is what we're talking about today. We're talking about a fourth and new technology that we proposed in 2017 that has all of the names listed there, but arose by any other name. And it is, as described in the video, a single pipe ambient temperature loop interconnecting boreholes and borehole fields to buildings that have a ground source, and actually it's technically a water source heat pump or an array of heat pumps that pulls off the heating, cooling, or both simultaneously that building demands. It is very essentially managed. This is a managed system. There is a central management and pumps for every loop that allows you to optimize the energy, the thermal energy over space and time. What do I mean by that? So just to start here, think of purple as containing really the potential for both heating and cooling, that ambient temperature somewhere in the around 55 in Massachusetts. And you've got a building cooling, but it's in the middle of the winter. And as it cools, it is rejecting heat. And that heat, because you have a single ambient temperature loop, is immediately reused. And so we call that synchronous load cancellation. It's a new type of energy efficiency. It's not unlike a VRF if you're familiar with it, except it's street scale. And then when you add the boreholes, yay, there's some boreholes. And just to pause for a second, we're typically assuming a closed loop vertical borehole, which is about 6 inches wide and has a 2-inch pipe in grout that goes down roughly 100 to 500 feet. So as you as you are, say, in the middle of winter and everyone's heating, or you're moving heat into the bedrock, you're using the bedrock as a battery. You're moving heat into the bedrock, both the near field and the far field. The near field you can use quickly, an hour later if you need it. The far field can hold for longer. It's your thermal battery. And say, oops, yeah, I guess I didn't have that. So say you have a lot of heat moved into the field in the middle of the summer and end of August. And then in October, you're starting to cool, you can pull that heat back out. And that we have data on from an install in Colorado. That's asynchronous load cancellation. So back in 2017, when we proposed this to each of the utilities in Massachusetts, we walked into the offices of the presidents of each of the major gas utilities and told them all about their impending death spiral. They didn't kick us out, having built a relationship of a certain amount of trust to allow us to continue talking. And instead, one of them, Eversource Gas, said, look, we need to know more, and gave us a list of all the questions. So we engaged with Bureau Happold Engineering, a global engineering firm, to do a feasibility study for what would each of these individual street segments look like in Massachusetts, and we had Eversource data to work with. And so one of the things that came out of this is that seasonal opportunity where in the hardest to decarbonize space, a high density mixed use, you actually have a balanced load seasonally. So the more you can store energy, the more you can cancel loads and you get an extraordinary energy savings. And of course, coming back to that electrification schema, now we have a way to take an entire street segment to network geothermal from gas, which allows for the customers to stay with the now thermal utility keeping the customer rate base fixed, even as you're evolving to meet the needs of the future to a decarbonization. So say, imagine you've got a gas utility. Today it's 1% geo and 99% gas. And in 2050, it's 99% geo and 1% gas. I'm optimistic. And the implications of that are even acknowledged by this report from E3 for the Massachusetts gas utilities, where a building by building off gas causes that death spiral and rising energy burden for low income, which is really the biggest concern. You know, the last people left on a system are not going to be people with the means to get off. The Germans, I believe, call this the last grandmother problem, where there's one grandma holding the bill for the entire infrastructure. Doesn't really happen that way, but we pay for it anyway, right? And so even in this analysis, the gas to geo pathway, in part, it was only 50% there, dramatically dropped the energy burden for low income customers and stabilized the transition. That's an essential component. And just to address the comment about cost effectiveness, so if you put in a ground source heat pump today, your payback period is long because it's a lot of infrastructure cost, or long for a residential choice. However, it is lower cost to operate today than gas because it's so much more efficient than an air source heat pump. I mean, just pause and think for a second. You're taking temperature, you're moving temperature. It's the same thing as your refrigerator, a heat pump. You have one in your home now, I guarantee. And you're moving temperature, but the air source heat pump is taking heat out of the coldest day of the year's air, and it's taking cold or lack of heat out of the hottest day of the year. And so it has to work really hard. Whenever you need it most, it has to work harder, which means more electricity use and less efficiency. When you use a ground source heat pump, even just a straight up ground source heat pump, you have none of that. You have really a nearly flat electric load demand because you are using the controlled temperature of the bedrock, not the fluctuating temperature of the air. So this is a projection from Applied Economics Clinic from 2019. We're actually in the process of updating it, and we'll publish another one soon. Just showing with network geo, with all the infrastructure costs versus gas, what the projected customer heating bills will be. And so just like ground source heat pumps, and especially because with the utility model, the utility pays the upfront infrastructure cost, enjoys the long-term payback, and the customer just gets to pay the bill. So the bills are lower. And then another really critical component of the system, you can see how we're just jumping across all of our different stakeholders right now, is the gas workers. So the gas companies and the gas workers have been one of the biggest opponents to decarbonization and electrification across the country. They fought a lot of bills. I'm not gonna say every, because that's probably not accurate, but you know. And gas workers have really high stakes because it's their livelihood, it's their retirement. This is what they're trained to do. A lot of them have high school educations and have good family supporting jobs. Those don't exist that often anymore. And certainly if they switch to solar, they're taking a steep pay cut and a loss of benefits. So here we have a possibility for them to have a totally horizontal transfer where they take the skills they have and they just switch the color of a stripe on the pipes. And you have a whole workforce ready to go. And they get to keep their retirement plans and their benefits and their good job and lifestyle. So guess what? The entire pipe fitters UA union, national union, has come out in support of this approach. They prefer the name thermal networks rather than geothermal networks. Remember our naming nightmares. But this video is a to die for video where they declare all of the dangers of climate change and then march in with their arms folded to solve it with thermal networks because they can build pipes. Totally pro electrification now, as long as it's with pipes. So this is one of my favorite outcomes or benefits or system solutions. And so most of the things that I've just discussed are really impacting particular sets of stakeholders. This one is one that people were missing because it's kind of a large scale. And we actually ended up publishing in Nature Scientific Reports this outcome with the name the Falcon Curve, attempting to be catchy because we needed to define the problem in order to show people how we'd solved it. It's very hard to solve a problem people don't know is there. And if you know the duck curve, I know a bunch of you are in solar, so the duck curve is scary, but the Falcon curve is way scarier. So this is January to January, US building electricity use on the bottom, residential, commercial, and industrial. And we did a magic wand thing and converted all of the fossil fuel, oil, gas, propane, et cetera, to electricity. But we tried it with different efficiency technologies. So if we magically transferred all of our fossil fuel use in buildings to a electric baseboard, which thank God we're not going to try to do, you would get this terrifying Falcon curve where in January you have a winter peak that is multiple times our current electric grid. Which means, of course, that even as we are trying with our RPS to decarbonize our electric grid incrementally and starting to build wind turbines, there's one up, we have to multiply that by 6, 7. That's harder. And so the more you increase the efficiency of the technology you deploy in building decarbonization, the more you land the wings of the Falcon, and it gets a little less scary. And so air source heat pump, COP of 2, these are, every one of these has a range depending on where you are, the weather, and the technology. But I just want to comment that the air source heat pump, the published and referenceable efficiencies are for a 47-degree day. And so what actually happens on that winter peak is not what the published efficiency is. It is much closer to that electric baseboard, which is a really important problem. And then your ground source heat pump, you've got increased efficiency, and then your network ground source heat pumps, where at that point you have, if you get to that COP of 6, coefficient of performance of 6, or a 600% efficiency, you start to see a really flat electric grid. And what this means is, one, you have minimal build out as you're transitioning your electric grid to renewables. And two, your load factor, which is the gap between the peak and the trough, is small, which means your electric prices for customers are low. It's a good thing. And the more that you have a huge trough, your load factor is bad and causes rising electricity prices. We already have high prices. So I'm sorry to spend a little too much time on this, but that's the Falcon curve. And that is, to me, maybe the most critical aspect of why to deploy the most efficient technology known today for building decarbonization. And I'm going to zoom ahead now and pick up the pace a little. So one of the wonderful gifts we experienced in the world was when we put out that feasibility study RFP, we discovered that there was an older group of engineers. They actually call themselves the gray edge group because they have the gray edge, who were ex-oil and gas and got into geothermal and kind of innovated and built almost exactly what we had described and pitched, but on a college campus. And there's quite a few examples out there. So this is Colorado Mesa University, and it's a chart that Xcel Energy, their local electric and gas provider, sent to them with a note that was basically what the they expected to have to build out electric capacity and had been preparing for it. And because of the growth of many new buildings from 800,000 square feet to 1,200,000 square feet, and there was no annual increase in electric load. And they just were like, what are you doing? And so not coincidentally, Xcel Energy now has feasibilities for network geo and has just completed, together with us, a case study of Colorado Mesa University. We're treating it as a living lab. It's an awesome little place out in the Mesa in Western Colorado. And here's a rough overview of the real outcomes from this 15-year in operation fabulous little example. It had a 10-year payback. They make about $1 million in energy savings. They dramatic carbon reduction. 100% of heating is covered. Water use is cut by 60%. That was one that we didn't see coming. We didn't realize that the use of chillers for larger buildings used so much water. And this is on the Colorado River. So that was one of their biggest outcomes, which we hadn't even predicted. And then here's that COP that we talked about. Their average annual COP is 5.7 with a peak in the winter of 8.9, which is, if you're in this space, utterly mind-blowing. So mind-blowing that we're taking a long time making that report because we have to back up everything because people were going to look at it and say there's no way. So I'm going to give one more small case study because we've got a lot happening in Colorado. They've now passed a law permitting requiring gas utilities to build thermal networks. And a group of Colorado students worked with NREL, National Renewable Energy Labs, to ask some questions, like for a typical Colorado neighborhood, which is this one that they decided to evaluate. What happens when you electrify by different technologies? And you can see that when you go electric baseboard, I know we're not going to do that, but it's 3,500,000 gigawatt hours per year needed to be built out. That's siting and sourcing new electric. And when you do the network approach, you actually cut your electric demand by 1,744 gigawatt hours per year. That's what we need. And they have a lot of electric baseboard there, so that's part of why it's coming out that way. But just to give you a sense of, these are just individual air source and ground source heat pumps. The ground source in green, the air source in purple. And here's that winter peak. It's another way of looking at that Falcon curve, the gap between the two when you are in that winter peak. And so they got some interesting fun results for the different types of buildings, what % reductions in site energy from baseline to network. And you can see that you've got some really good reductions for schools and hospitals and other critical buildings that would, of course, enjoy the resilience as well. And here's the summary, that the baseline here, and then electric baseboard, air source heat pump, ground source heat pump, and network. And so needless to say, Colorado is moving forward. And a lot of others are too. So I mentioned Xcel Energy. So I just pause for a moment and think about how many gas utilities you think are signing up to go beyond gas, to move beyond gas, to build, to decarbonize and get off gas. So, oh, we've got an echo. So the shocking, but yet not shocking given the actual economics of this, because it's a better business model, is that we have 23 gas utilities currently engaged in this pathway from gas to geo. And recently, when 10 of them showed up in Framingham for a tour of Eversource Gas's install, one of them said, I don't know a gas utility that isn't considering this. So here they are leading. Our advocacy network is a little behind. We're trying to make this a little competitive. Our approach to trying to drive the national change is to build networks of all the core stakeholders across the country and then intersect them in each state. So here's our advocacy network. And then here's where legislation has been passed permissioning this gas to geo transition, passed, filed, and considering. We've got a great piece of legislation, third in a series here in Massachusetts, the future of heat, clean heat. And then here are where there are installations. And I want to point out something quite quite remarkable about this technology as well. So I mentioned the folks we found, the Gray Edge group. Well, the ground source heat pump is actually an American innovation, and it comes out of Oklahoma and Arkansas. And so the very first projects that we have been able to find over time are actually in Utah, Colorado, Texas, and Iowa. This is a red state friendly decarbonization technology. And in fact, geothermal is favorably viewed by Republicans across all of those states. People often think, hey, they're doing it in Europe. I get that all the time. Well, why don't we learn from Europe? And the curious thing is that, oh my gosh, Europe is so far ahead in so many things. And they've got amazing district energy. And I think that's where the confusion comes, because they have first generation, second generation, third generation, and fourth generation district energy. But this technology, which they call fifth generation, is brand new there as well. In fact, we're leading here in the US. So this is how we got to this article this past June, where the first ever gas utility installation of network geothermal in the streets, not on a campus, actually in the streets delivering to multiple customers, broke ground in June. And gosh, I love the pictures. The loop is currently today in the street, nearly complete in the street, and they're still working on boreholes. I have so many pictures and videos, but I had to cut them. And they ironically couldn't find pipe that said geothermal, so they stenciled it, which to me just felt so classic 1800s gas company. I love it. And so here's a quick map of the system. It's got 1 mile of main and a loop around the neighborhood. It's got a fire station, a school, a whole bunch of residences, some commercial buildings. My favorite one of all, people, is that there is a gas station in Framingham who is going to be heated and cooled by geothermal. So we at HEET wanted to ensure that when this project and the 5 others permissioned in the Massachusetts with National Grid and in Merrimack Valley, we wanted to make sure we're actually learning more rigorously than a typical utility evaluation. And so we founded the Learning from the Ground Up research project to try to get the kind of data we need to plan forward and to fully understand and optimize these systems. So our Learning from the Ground Up team has two national labs and a whole bunch of local experts participating, and we're founding an open database of the projects with normalized data. We're putting into law across the country a requirement to contribute to the database, tee-hee. And we've got building a library of tools and resources, and we are building core models based on the projects going in the ground, and then refining those models with all of the data we're collecting, and then calculating from the models and the data the impacts of the installations and what we can do to scale and drive change. It's kind of an enormous project, but we tend to define things by what is needed and not what we think we have the capacity to do. So here's a quick update to NREL, which they just completed their first iteration of our reduced order model. It's got all of the components. The ambient temperature loop does not yet have the thermal loop physics included. That's next stage. And we've got some results out. Here are the 3 bore fields designed in the Eversource project. And we've got the change in temperature as the water travels around the loop, and it's balanced and stabilized. And so that's kind of awesome to see. And this is a way to look at that Falcon curve again and look at the power, the energy used. So you've got in the green, you've got the heat moving from the boreholes into the loop and out. In the blue, you've got the buildings moving the heat into and out of the loop. And then you've got your electricity use in the pink. And that is exactly why the system is making a lot of sense, because you're balancing annually and minimizing electric impact. So this is also a leg up team result. I just had to add it because man, it's a little messy out there. And we are putting fiber optic cable into a bunch of boreholes in order to have continuous monitoring. And I see a hand went up, but I'm almost done, and I'm going to just finish off quickly. And I will pause for a second, because I thought after all of that, I'm going to pause and say that it's time for coffee. But what I mean is actually it's time to ask you a question. So just pause for a moment, look at this coffee, and tell me if it's hot or cold.
Looks cold.
And
It's
I like
full.
I like that you boldly threw out an answer.
I don't see any steam, right?
Well, that's true. You didn't see steam and you don't see ice, so there's no phase change
Yeah.
happening.
It's an ambient temperature.
But you don't know the temperature.
Yeah.
Ambient.
You actually don't know the temperature because we can't see temperature. We can see phase change, but we can't see temperature. And so to me, I think this is why we're missing thermal in our approach to decarbonization, is because we can't see thermal. And what I propose that we need to do, and what the leg up data and from the projects and all of the advances across the country need to inform a fully tactical thermal transition plan at every state and community, where we look at our electric grid capacity, assets and values, the gas system capacity and asset values, the dependency ratios on the gas system, the hydrogeology. I won't read all this, I promise. Thermal sources and sinks, where there is thermal opportunity, basically everything. And we create an algorithm between these that optimizes the deployment street by street of which technology, when and where. And that will allow us to minimize the impacts of decarbonization and maximize the benefits. And just to draw your eyes to that unseen thermal, there's rejected energy here on the upper right. This is a thing that Lawrence Livermore National Labs produces all the time. It's a Sankey diagram of our entire energy system for the US. It's cool. And when you look at it, the thing that struck me so much was the gray, because the gray is all of the rejected energy, the wasted energy. So we consume so much energy here in the US, and we use less of it than we waste. So a huge portion of that rejected energy is thermal. And when we start to see it, when we start to plan how to capture it in all our data centers and our sewage and our every community, when you begin to look, has thermal opportunity. Here in the, I will go off on thermal opportunity for 1 second. So think first, here's something to push your kind of Overton's window out. Boston Harbor. The lobsters are getting unhappy, and a lot of us like to eat them. They're moving north because Boston Harbor is warming faster than a lot of other places. And if you look at the temperature change in Boston Harbor between pre-climate and now, and ask, with its turnover, how much temperature could we pull off Boston Harbor, and how much of Boston would that heat? Then you go and you order some lovely titanium seawater industrial size heat pumps, put them under the docks in Boston Harbor, and begin to solve the lobsters problem while heating our town. That's what it means to take a look at thermal opportunity. And we're trying to get that to happen at the federal level. Here's a photo. I'm like, I think the shortest person here. And somewhere in there she is Secretary Granholm, who says she loves geothermal. So we're trying to hold her to that. But the good news is that there's some numbers behind the love. The Inflation Reduction Act just made ground source heat pumps incredibly affordable, and in some cases, often in schools, a least cost first option. And there's also $245 billion we can tap into for the gas to geo transition. We just have to move. And so this is my last slide, and it's actually an image of our gas system here in Massachusetts. There's no labels, so I'm not breaking any rules with the security. But it is, it was in the 1800s that the first pipe went in the ground. and I have wondered if those people putting that first pipe in the ground imagined how long it would last and how complex it would become and how big it would grow. And there's still one of those pipes in the ground, unfortunately. Out in Beacon, there's a pipe from Lincoln's time. Yes, President Lincoln. And what we now have is geopipe in the ground today. And here's the president of Eversource's quote about this. He said that he acknowledged that the technology could eventually supplant a significant portion of the company's natural gas network. He said that's okay. One displacing the other is not a scary proposition. It's an exciting proposition. And to me, socio-technical system change means we need a good technical solution that is real, that addresses all of the concrete problems, but it's not going to happen unless the people do it. And so this alignment with people who can do it is why the change is happening. So go ahead and scan this QR code if you want to say you want geoservice on our little map. And everything we have, all of our reports and everything, is open source under Creative Commons. I will now unleash the opportunity for questions.
Great. Zeyneb, that was wonderful perspective, and I want to thank you for a really magnificent presentation. I'd like to lead off. I have an observation and then one social and one technical question. The general observation is that people have, from the very beginning, chosen to use the most abundant sources of energy to meet our energy needs. And for much of our history, that's meant fossil fuels, oil, natural gas, and so on. But I think it's still a worthwhile view to take the position that we should use what nature has provided us in most abundance. And to me, that means sunlight, it means water. And I like the concept that you've introduced here of a natural battery in terms of the available heat that is provided in terms of the earth. I think those are all abundant resources that we have to tap, and there should be some mix. And what that mix will be, I think, is an open question and one that requires some long-term vision. But having said that, I have one social question. You've shown us how effectively you've been able to introduce geothermal networks into Framingham. I'm just wondering about the way you've approached the public. Change is always difficult for people. How did you manage the public, the outreach to the stakeholders in Framingham to make that happen? And then secondly, I have a technical question. When you talk about replacing or retrofitting or whatever the right language is, the piping that is used for transport of gas in our neighborhoods, with piping that will transport water, there are major differences. They may both be carbon steel, but you have totally different issues associated with natural gas than you do with water. Yes. Water is corrosive. It can cause embrittlement in some cases as a consequence of corrosion. On the other hand, natural gas is not really corrosive. It's not an electrolyte, but it does have embrittling properties if you use the wrong material. So my general question is, what are the materials of construction that you're using in Framingham? I'm just curious.
Okay, I'm going to go back.
That's a lot. That's a lot.
Yeah, no, it's great. It's great. I knew this was going to be fun. So I'm going to go backwards. So on the piping, it's not actually steel, though the Danes tell us we should be using it, and I may agree, but it's HDPE plastic. Density polyethylene, which is what we currently use for gas pipe. So our gas pipe going in the ground is HDPE plastic. It's butt fused or thermal fused. You know, there are a lot of problems with the gas system. I can go into it for a while with regards to also there's components within our gas that are not methane. Methane, of course, is kind of a known quantity, but there are over 100 other chemical components in our gas supply being delivered to our house, including benzene, but also including some solvents that we believe are coming from the fracking system. So the water in the pipes, there's several installs that just water, but actually Framingham is using water with glycol to reduce risk because they're a utility. And there is actually a thorough expectation that the pipes will last far longer than their expected lifespan. And if you think about our actual water system, which we have all around us, it's lasted over 150 years. Questionably, it needs some repair, but that is basically what we're installing, is not.
Well, let me just ask a question. And in terms of plastic piping, there are issues associated with joining piping of that kind. Have there been studies in which geothermal sources have been used to demonstrate that the joining operations can be performed successfully and with long-term durability?
It's actually a hell of a lot easier with the geothermal piping than it is with gas. Gas, of course, combusts.
Yeah.
And and leaks, great climate impacts. But yeah, there's actually geothermal ground source heat pumps have used the same piping with the same fusing since the 80s. And they have had no problems. In fact, there are still systems operating with zero problems. One of the problems we have run into with workforce stakeholders is that the documented operations and maintenance of the system is so much lower than gas that they are concerned about their livelihood.
Yeah. We're going to have a presentation in January by a gentleman from XGS Geothermal in California. I don't know if you run into them at this point, but he will address some of these issues as well during that presentation. But it's something that's been on my mind.
He's probably going to address hot rock geo, which is going to deal with high temperatures, which really does have a challenge around the components and the materials use.
Yeah.
This one, you're ranging between 40 and 90 degrees temperature, water with glycol. The challenge to the components is so minimal. This is old technology in that way. And so,
just the final comment on the technical issues. I'm glad to know that MIT is involved. Have you run into a fellow named Paul Waskoff?
No.
You have?
No, I have not.
Oh, he's very interested in geothermal boreholes.
Yeah, well, I'd love to.
Paul Waskoff, WSKOV. He spoke to us a couple of, maybe a year ago.
And I will just briefly comment on your social question.
Okay.
And I think the very first image I showed of the stakeholder engagement is really critical.
Yeah.
That if you are selling something that people want, it just means you have to communicate clearly because you've aligned with their core needs.
Sure.
And so the inherent design of the solution with regards to the core needs of the stakeholders means that all you really have to do to engage and get people aligned is to communicate as clearly as possible and as kindly as possible. And so that's what we do. And we try to do it at different levels in different languages with different ways, images and so on, and build relationships, because no change happens without people, and people change because of relationships, not because of data, as I'm sure you've all experienced.
Yeah. I think of the analog with the siting of nuclear waste repositories in the United States, which has become a very difficult prospect. And part of the problem is that the stakeholders had not been involved in the way they should. So, I mean, in your case, do you have town meetings? Did you have
we had all kinds of things. We host charrettes that are open, that engage all the stakeholders together. Actually, our first charrette was at MIT in 2019. We've done a summit actually also at MIT with 300 people, and that one had the then Attorney General. And we do just an endless number of one-on-one and small group presentations.
That sounds very smart. I like that.
Yeah,
that's very good.
And I want to comment one thing. I see more questions of, you mentioned the abundant energy and why we go for fossil fuels, and I just can't help myself. I think there's this fascinating idea out there about an extension of the laws of thermodynamics that apply and connect biology, and the idea that we, biology, are inherently evolving to dissipate energy, that there's a relationship there. And to me, that is connected to the idea that we consume abundant energy. And what makes me optimistic is that wind, solar, and the geothermal energy I'm talking about, it's just stored solar energy. It's millennia of solar energy stored in the bedrock. And all of those are more abundant, more ubiquitous, and lower cost than fossil fuels. And I think that is actually why we're going to succeed.
Well, and also green. I mean, I think it's clear that our climate has changed and we've got to be serious about that. But I don't want to, let's turn to some other hands. Michael. You're okay.
Are you familiar? First of all, I thought this was a tremendous presentation, and I really like the way that you pointed out how we transition the employees of the gas companies from their current situation to a brighter future. Are you familiar with Smith College's program out here, where they're okay. Are you involved with that?
Yeah, we were meeting with the then sustainability director, who's now at Tufts. When they began the planning process, they're working with a company that we work with closely that actually just did the reviews for National Grid. And we're very excited about it. We tried to help them get a wastewater thermal recapture permit from the DEP.
I think Amherst might be next also.
Actually,
one last question.
Williams, UMass Amherst, there's a ton of them.
Oh, okay, great. In the bottom line, does the utility make more money on this? Does this increase the utility's profit?
Oh, yes. Why do you think there's 23 of them lined up? Yes, here's how it works. It's kind of beautiful. It's called a steel for fuel. They are putting more infrastructure in the ground. One thing people don't always know about utilities is that the utility model was designed over 150 years ago to build infrastructure. And so the only way they make money, they don't make money on selling you gas or electricity. They make money on the cost of the infrastructure that they built. They get a 10% guaranteed return or something like that on that infrastructure. So their entire incentive is to build more infrastructure, which actually has sucked for us for the past 50 years. But now it's actually useful again. And when they put in this infrastructure, it costs more than the infrastructure for gas. So they make more money. But then, because you eliminate the cost of fuel on the customer side, the customer pays a little more for the infrastructure, but less for the fuel, and ends up with a lower bill. So you actually have a win-win. It's called steel for fuel for an unknown reason.
Let me just ask you if there's one other possibility in your own mind. Out here, I've formed a company, and a certain portion of our profits and equity actually is going back to the community to link the energy sector with the health of the social sector, which gives a long-term guarantee that the social sector always have a certain amount of income to deal with housing and poverty and these issues. Is that something you might be interested in knowing more about?
Oh, absolutely. And I want to kind of comment. I see some chat comments as well. I love the locally owned energy system. And there's a bunch of them in some of the European countries, and they make a lot of sense because that 10% profit goes right back into the infrastructure and the people. And that's beautiful. We had a really hard time tackling the question of whether to prioritize this as a gas utility, existing investor-owned utility transition, or to try to drive forward municipally bottom-up kind of installs. And it is fundamentally practical, if we want to get this done, to use the power and financing infrastructure we have today. We could not, there were minimal opportunities at the municipal level. We have an existing socioeconomic system that we're working within. What I will say is that this system lasts long enough with low enough O&M that 40 years from now, it will no longer be an attractive asset to a utility and will likely be sold to municipalization. And that's the model we're approaching, is that we're going to have to use our existing investor-owned utilities to drive a substantial portion of this. Any muni or local community that wants to build it, we're ready to support and help. But so far, the scale of interest is dramatically different.
Thank you.
Walter.
Yeah, so I got a question that segues into that. In regards to Great presentation, and especially from an maybe even maintenance standpoint. But you haven't addressed the capital cost. So on a per I guess it wouldn't be kilowatt hour basis, maybe BTU basis. Um, what are the costs, the relative cost, capital cost now? That would be, and you mentioned that it'd be a higher rate that our utilities would charge for the infrastructure. So have you estimated what that cost would be? And I imagine the cost would be different depending on whether it's a city setting that's heating and cooling a large building and a residential section. And then are these systems mostly for a newly built neighborhood or existing neighborhoods?
Oh, great questions. Thank you. So first of all, they are actually ideal for existing neighborhoods, which is the hardest to decarbonize because of the ability to move. If you have a building that's historic that you're not able to weatherize as well, you just increase the thermal delivery, which is a great way to solve existing building stock. New buildings, it's a lot easier to build efficiently enough through passive house to make this less of a useful payoff. So existing building stock. And then coming to your cost question, it's a critical question. So we have a number of costs for the infrastructure install from the college campuses, but that's substantially different from installing in the right of way in the street in a community. And what we have so far, we have projections from Bureau Happold Engineering. So currently in Massachusetts, or rather a year ago in Massachusetts, a mile of gas pipe is on average like 1.7 million, and in downtown Boston, it's like 4.8 million. So again, yes, harder in the city.
Wow.
The estimate initially for doing that with geothermal pipe instead was 60% more on with that same difference between rural and city. And so that's where we got our projections for the cost for the customer. Of course, the key thing is that the rate makers get to decide. So if the rate makers decide, hey, we've been amortizing the gas pipe for 40 years, but with geopipe, we're going to force you to amortize it for 20 years, then the price goes up. Or they say, hey, the geopipe is rated to last for 70 years, so we can amortize it longer, it goes even lower. So I just want to qualify that this depends on the regulators. We have assumed identical to the gas amortization. What's actually happening in the ground out in Framingham is a beautiful case of the learning curve and the innovation curve, and the prices are going to be much higher because everyone out there is doing it for the first time. And so what we're trying to do is get as many projects going with all of the cost calculations to be able to start to appreciate what an average cost will be at the other end of that learning and innovation curve. I hope that answers your question. We have some reports we can share.
It answered my question, I guess, qualitatively, but not quantitatively. Right now, with our electrical cost here in Massachusetts, the transmission cost is about 17 cents a kilowatt hour, whereas generation at the present time is probably about 14 cents a kilowatt hour. So the transmission costs more. So in your model, quantitatively, how much is the distribution cost?
I do not have it in kilowatt hours, which actually I think we should. I think we should make it comparable. But basically, it's not the same system because you've moved transmission and generation into one local system. You don't have the same losses. So what I guess I was saying is you're eliminating the generation because you're not combusting anything. You have no fuel. Instead, you're just doing delivery and transmission. So the infrastructure costs are the costs that the customer.
You have some fuel. You have some electricity. I mean,
you have the electricity
pumps
of the heat pumps and the
heat pumps
system.
sure.
Yeah. So we have economic projections that estimate that And like I said, it came out at about 60% more than the price of the gas pipe in terms of infrastructure costs going in.
Yeah.
So
I had a quote at my house for geothermal,
yeah,
and it was about for standard size house about $60,000-$70,000, and whereas air heat pumps were less than half of that. And
yeah,
so I couldn't justify geothermal, at least in my house. Now I understand yours is a neighborhood system,
oh,
so it's a shared cost.
that's
But
how I
but still,
started this.
but
That's
still, that needs to be quantitative. And
I
so,
agree. So that's how I started this, is that I wanted ground source heat pumps because it seemed like the most efficient way to do this for my house. And I got the quotes and it was like $50,000 for a borehole. And I'm like, I can't do that. And I asked how I could get the price lower, and they said, well, you know, if you can get your neighbors to bringing the drill rig is a big part of it, so we can cut you up this. And anyway, long story short, I couldn't convince the water department to let me put a pipe in the pond. And
yeah,
so
I got yeah.
I actually can tell you that the payback for the infrastructure for at least 4 projects that have been operating for years is 10 to 12 years. And for a utility, for a personal customer, that's actually kind of rough, 10 to 12 years. But for a utility, that's pretty great. It means there's a profit margin in that 40-year payback and a margin for the customer cost to go down.
Hey, what just one more a brief thing. The Boston Globe did an article on the Framingham installation. You're probably aware about that. It was either today's Globe or yesterday's Globe. I'm not
2
sure.
days, yeah, yesterday.
Okay, yeah. And so everyone pick up yesterday's Globe and take a look at it. Very good.
Yes.
Thank you.
This is an important discussion you've just had. I want to make sure I've captured it or understood it before I turn to Albert for his question. So it's an interesting point. You do not have generation or distribution problem issues in the same way you do with a traditional fossil-based utility or any other utility for that matter. There's always a generation and distribution charge. In this case, with a geothermal network, the source is local, but am I correct in understanding that by scaling it up from an individual homeowner to a network of homeowners, that's the mechanism of reducing the costs? Or is it the utility that's bearing the cost?
So there's multiple mechanisms that we're kind of building like a layer cake. So one, you do have the opportunity for kind of just scaling efficiencies with the utility in terms of ordering, like, you know.
Yeah.
And you do have, but the part where I showed the energy synchronous and asynchronous load cancellation between buildings.
Yeah.
So there's a Swedish utility that built just a plain loop, Eon, and they documented 30 to 40% load cancellation simultaneous with no boreholes. The Colorado Mesa project is showing sometimes 50 and 60% load cancellation. For the entire shoulder seasons, they're basically coasting without drawing from the boreholes. So that phenomena is what's driving the efficiency that makes the infrastructure worth installing, as opposed to that individual ground source heat pump, which is not a bad thing, but never achieves the efficiency that a well-designed thermal network can.
Thank you. Thank you. Let's go to Albert.
Yeah, hi, Zeyneb. It all looks good to me, except for all these boreholes that you're going to make, which are expensive, and I probably have other issues.
Yeah.
How does that compare with a deeper single hole, going back to what you call the district heating system?
Right.
You could service several homes via a district heating concept with one borehole that goes deeper.
So that's an awesome question. And there's a couple of installs out there that have one deep borehole. There's some in Paris, and they have a little more geothermal resources, so they're getting hotter temperature from that one borehole. The short answer is that those one deep boreholes are actually a lot more expensive to drill and much more risky. And so these other ones, as some of the hot rock people say, they're like, oh, you're doing the pinpricks. I'm like, they're not pinpricks, they're 500 feet deep, but they're really the same thing as water wells in terms of size and scale of drilling. And so at the moment, the costs, but for doing an array of closed loop vertical boreholes that are about 6 inches wide versus doing much deeper they're just better right now. That said, this is a perfect place for research, and there's so much potential. I personally like concentric boreholes better than U-tube boreholes, and I can't wait to try one. But we actually have 2 types of boreholes out in Framingham we're studying. Celsius Energy from France is doing a kind of dandelion-shaped diagonal boreholes that are a little deeper on one field, and then the classic version on the other fields. And we're so going to compare the data and the costs and figure out what's happening there. I also will just say boreholes are great for using the bedrock as thermal battery, but other thermal sources are awesome too. And there's a whole bunch of thermal storage in development that might be lower cost. There's a lot of opportunity once we start looking at thermal and how we can play with it.
Also, on the thermal battery with the earth, returning the heat to the earth, but the pressure is higher at the base of the borehole. So how does heat go back?
So you have you're moving water through a 2-inch U-tube that's set in a very thermally conductive grout. And the water is pumped into the borehole at a rate and pressure that allows it to return up. So the moving water is causing thermal convection into the bedrock. In the near field, it happens quite quickly. And what you do is you do a thermal test to do transmissivity. And then over time,
ready to go.
Sorry. Over time, that near field begins to
You can listen to that if you want.
into the far
I'm
field.
sorry, Zeynep, if folks who are not speaking could mute their microphones, that would be great. Thank you. Go ahead. I'm sorry.
No worries. So the near field thermal transmissivity and convection then slowly drifts into the far field, which is further away from the borehole and the bedrock. And there's a bunch of people that are actually studying when you have water flow, you can also have thermal drift further out from the bore field, which can be an advantage or a disadvantage depending on your design.
John.
Thank you.
I was wondering about how it's been worked out with the individual building owner, homeowner, whatever. There's all kinds of different HVAC systems in different houses. So, you're giving them the input of the water from the geothermal, but how is it being designed? You got 100+ customers, and probably every single one, there's probably some of them that's just perfect. They already got a system that's just completely compatible. We just plug it in, and there's others that have a system that is probably not at all compatible. Who is doing the design? Who is paying for this, et cetera?
So the classic shortest answer is it depends. There in the demonstration projects that are happening now across the country, we're pushing very hard to have those demonstration projects have integrated provision and design of the HVAC transition, because you want the sizing to be right, and there aren't standards and codes setting that for a thermal network yet. There will be coming soon. And so each of the demonstration projects is providing the HVAC transition to the customer with no upfront cost. And to me, that is how the transition is going to happen. If we don't do it that way, to some extent, renters, low-income people will be left behind. So if we do that, and we either do on-bill financing or we do amortization, however we do it, and that allows for the sizing to be actually directly and correctly designed for the water source heat pump for the loop, which is critical in the beginning. Again, 5 years from now, we should have much more standard ways to control it, and control good designs. But within the house, it depends on what distribution system you have. So that's the replacement of the boiler with the water source heat pump, which, by the way, is factory sealed, lasts longer than an air source heat pump, and doesn't leak refrigerant as often. But then if you have a steam distribution system, it's never going to reach that heat unless, well, there's some prototypes out with carbon dioxide in the heat pump that can hit it. But really the market-ready heat pumps, water source heat pumps, any kind of heat pump can't do steam. And so you need to transition to forced air or forced water. If you have forced water, it's actually the most efficient. And you can connect easily with geothermal to either forced water or forced air. Again, though, every house is its own story. And there are plenty of houses where the distribution infrastructure is poorly designed, over-designed, under-designed, and it's always a good idea to assess it properly and adjust it as needed to the system.
Zeyneb, I always promise our speakers that we'll end by 12 noon so that you can get back to your day job. But I want to thank you for a wonderful perspective on geothermal networks. And I also want to give you an invitation to your staff. I hope that some of your folks may have an opportunity to join us in our future meetings. As you can tell from this conversation, we are intensely interested in this subject of the electric grid and climate issues, and I would just welcome your participation going forward. So if you have time or your staff, you have the connection information on our link to the forum. We welcome your participation.
Mm-hmm.
Great.
I appreciate that, and it's a great group. Thank you so much for having me.
Well, the thanks is all ours. So thank you for joining us today.
And I will just comment that I see a lot of comments from Drew. And Drew, I'm happy to talk at some point after. I'm going to put my email in here. I'm not a fast reply on email, but I will.
Okay, very good.
Okay. Thank you.
Thanks, everybody.
Bye-bye.
See you in 2 weeks. Take care. Bye, folks.